In this video, we will discuss games and gambling. An example, a player pays $3 to play the following game. He tosses 3 fair coins and receives back payoffs of $1 if he tosses no heads, $2 for 1 head, $3 for 2 heads, and $4 for 3 heads. Find the player's expected net winnings for this game. The solution is, for each possible event, net winnings are the payoff minus the cost to play. The sample space is tails, 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 heads, tails, heads, tails, and so on. So we determine very quickly that there is one case where all are tails, where there are 0 heads. The payoff will be $1, so the net winnings are negative $2. That's the net winning, that's the payoff minus the $3 that the player paid to play. So, and the probability is 1/8. If there's 1 head, there are 3/8, that'll happen 3/8 of the times. They get $2 in payoff, but they have to subtract dollars, so they lose 1 overall. If there are 2 heads, that happens 3/8 of the time. The payoff is $3, which means that they break even. And the probability is, again, 3/8. Finally, if there are 3 heads, that can only happen once. They win $4, but that means they're really just getting $1 back on their original investment. So the probability is 1/8. They make $1/8 here. We add up all of these products and discover that the expected value for this game is 50 cents. A game in which the expected net winnings are 0 is called a fair game. The game in the last example has negative expected winnings, so it's unfair against the player. A game with positive net winnings is unfair in favor of the player. Another example, the $3 cost to play in the last game makes the game unfair against the player. What cost would make it a fair game? So the expected value of the game is negative 50 cents. The cost to play the game is 50 cents too high. If the game cost 50 cents less, $2.50, it would be fair to play. We verify this. The net winnings become $1.50, 50 cents, negative 50 cents, 50 cents, and $1.50 respectively. So, and the probabilities don't change. So if we add all of these up, we wind up with 0. Another way to calculate the fair cost to play is to find the expected gross winnings. Gross winnings are the payoffs alone without the cost to play subtracted. If we take the gross winnings of this game, $1 time, we take the estimated gross winnings of the game, or the expected gross winnings of the game, that adds up to the fair cost to play, $2.50. In a state lottery, a player chooses 3 digits in a specific order. Leading digits can be 0, so numbers such as 028 and 003 are legitimate entries. The lottery operators randomly select a 3-digit sequence, and any player matching that selection receives a payoff of $600. What is a fair cost to play the game? We compute the expected gross winnings. There are 1,000 possible 3-digit sequences, and only 1 is a winner. The other 999 have no payoff. So the expected gross winnings are $600 times 1 over 1,000 plus 0 times 999 over 1,000, which is 60 cents. The fair cost to play the game is 60 cents. Now, state lotteries are unfair games. The profit made by the state funds benefits covers administrative costs and generally goes into coffers to keep the state's assets liquid. People play to beat the odds and try to make some money, however unlikely. Likewise, casino games are unfair. Casinos are businesses, and while the chances of winning are better than those encountered playing the lottery, the casino is run to make money for its owners. There are no fair games. One simple type of roulette is played with an ivory ball and a wheel set in motion. The wheel contains 38 compartments. 18 are black, 18 are red, and 2 are green. The player places $1 on either black or red. If the player picks the right color, the payoff is $2. Otherwise, the payoff is 0. Find the expected net winnings. So whether red or black is chosen, there are 18 chances for the player to win and 20 to lose. Using the expected value formula, the expected net winnings are $1 times 18 over 38 plus negative $1 times 20 over 38. So that is negative 2/38 of a dollar, which is negative 1/19 of a dollar. So there is an expected net loss of 1/19 of a dollar, or about 5.3 cents per play.